So in the previous class, we concluded the chapter 4, the process architecture. Um, so, so now we will learn about the memory hierarchy. So which means that in chapter 5, so we will learn about the memory systems in computer system. Okay. Then, so then what is the memory? Actually, we learned about the memory system in chapter 2. Actually, all data, including data processed by our program, also the program text, which means that instructions are all stored in the memory. Okay, so, and then this memory is called main memory. Okay, the main memory. So in the computer system, all of our data is stored in the memory, and then as we learn, the computer programs fetch, which means load our data from the memory to register file, and then using the arithmetic and the logical instructions and other instructions, these fetch data, is loaded data, are processed by instructions. And then these processed instructions are also written back to the register file. Then the data, the processed data is stored to the main memory, right? That's how our programs work in the computer systems. So I believe you understand the all of our data is stored in the main memory. Also, then where is our memory in the computer system? So I saw this actually. I updated the PDF file this morning. Okay. So where is the memory? So just to see the slide, so screen. So actually in the computer system, so the memory is here. So this board shows the main board of the desktop computer system. So actually in this board, so on this board, we so here we equip a CPU. So CPU is a processor, and then so you can find these slots. These slots are memory slots. Okay, so these are memory slots, and then actually these slots are called DIMM slots. Okay, so actually memory has the form of the DIMM form factor, and then we just insert the memory DIMMs into these slots. So actually in the computer system, the CPU is here, and processor is here, and then memory is here. So, but as you can see, the size of the processor is very large. Also, the size of the memory is very large, right? So actually in chapter 4, so where are memories actually? So in chapter 4, we learned about the process architecture. So, and then in this process architecture, we can find two kinds of memory: instruction memory and data memory, right? So that's what we learned until now. So about the memory system in the computer system. So we learn all of our data are stored in the memory, the main memory, and then actually the main memory in the real computer system, the size of the main memory, so actually the physical size, the form factor, the physical size of the main memory is very large. But in chapter 4, so we learned that the memories are the instruction memory and then the memory are included in the process of architecture. So in a real computer system, it's separated, it's physically separated, But in chapter 4, we learn, oh, memories are included in the process architecture. So what does that mean? So actually, in the real computer systems, memories are organized as memory hierarchy. So hierarchy means the 계층 구조 in Korean. So which means it is like there is a king in the top of the hierarchy, and then there are some number of people under this king, and then also there are some normal people, the number of people, something like that. So actually, we call this is a hierarchy. And then in the computer system, memories are also organized like this hierarchy. And then we call this memory system is, we call this memory system memory hierarchy. So why do we organize memory system as memory hierarchy? So which means that memory is organized like this one. So it's like the top memory, and then it's a lower memory. Okay. So, but when we learned about the process architecture, we learned that there are two kinds of memories. Memories are located inside of a processor, but actually, so this is the different kind of memory. Okay. So I will explain. So people introducing about the memory system, I will mention the locality. So locality is called 지역성 in Korean, but I hope you can understand the meaning of the locality. So the locality means that some kind of data. So actually, our program access data in memory, right? But our program actually normally when our programs access data in the memory data, we can observe some characteristics, some unique properties. And then these properties are called, this property is called locality. It's a locality. So locality means that if some material is equally distributed in some space, then we call this is the equally distributed. So which means that there is no locality. But locality means that some parts of material will be accessed frequently. So that is the meaning of the locality. So I will explain the detailed meaning of the locality. Actually, there are two kinds of locality: the temporal locality and spatial locality. So if we see the English word temporal, so which means that it means the time. It's a kind of time related. And then if you see the word spatial, so actually it is originated from space, so which means it's a kind of space. It's a space related. It's a 공간. Okay. So there are two kinds of locality. So and then I said that locality means that the data is accessed more frequently, or some kind of data is accessed more frequently. So which means the temporal locality is a time-related locality. So temporal locality means that if a certain data is accessed, and the same data in the future, in the near future, the same data will re-accessed. So which means that we referenced. So in our program, what does that mean? So it means the same data is repeatedly requested by load instruction again and again and again. So, and then this kind of properties is observed in our normal applications. So, for example, so we frequently use the iterative loop I equals 0 and then I less than 100 and I plus plus. So in this iterative loop, the variable I is repeatedly used, right? So you can find that the I we just change update the value in variable I, but this variable I is repeatedly used. So it means the same data is repeatedly accessed by a program. So this kind of locality is called the temporal locality. So you need to understand this meaning of the locality. So temporal locality means that if a certain item, a certain data is accessed, then in the near future, the same data will be accessed again. Okay. So we can find the instructions in the loop. So this is the loop. So actually, we can find several instructions inside the loop. Okay. And then also we learn that instruction the data. So which means when these instructions are repeatedly executed, so which means instructions are requested, the same instructions are requested to instruction memory. So memory, right? So it's called the temporal locality. Also, some variables like I, the index of the array. So we can know that in the iterative loop, this I is repeatedly used, repeatedly requested. This is the temporal locality. And then another kind of locality is the spatial locality. I said that this is the space-related locality. So it means when the data is accessed, and then in the near future, neighbor data. It's not the same data, but in the near future, with a high probability, our program will access the neighbor data. Okay, so temporal locality means that the same data is accessed again and again. It's a time related, but spatial locality means that when a certain data is accessed, then with a high probability, our program will access the neighbor data. Okay, so this kind of property is also observed in our program. So like this, AI equals BI plus CI. We frequently use the array computation, and then actually when this array is computed, then I is also increased. Then we can find that when the A0, the first A0 is accessed, and then in the near future, we can estimate that A1, right? It's a near data, so neighbor data. So firstly, A0 is accessed, and then A1 will be accessed in the iterative loop, right? If we use the array data, then we will use the whole elements in this array data, but elements are accessed from 0, 1, 2, 3, something like that. So it means neighbor data like A0, A1, and A2. So neighbor data will be accessed in the near future. So this is called the spatial locality. Okay. So to summarize, the locality means that the same data can be accessed again and again. Also, the neighbor data, when a certain data is accessed, the neighbor data will be accessed with high probability. That is the locality. Then why did I explain this? Because memory hierarchy, as the in looks like this, the memory hierarchy, exploit the memory hierarchy utilizes the is locality, the temporal and the spatial locality observed in our normal programs. Okay. This locality is frequently. It's a frequently observed. But as I explained, you can think that it is obvious. So right. So which means because certain data is accessed, we frequently access this data. Also, a certain data is accessed, we frequently access the data. And actually, it's the same to our real world, right? So if you start studying computer architecture, and you will continue studying computer architecture. So it means you will read the computer architecture book again and again. And then if you read some series of books, then you will, if you read the book number 0 and actually book number 1, then it's actually the next time you will read the book number 2, right? In the view. Actually, it's the same to the actually it's similar to our real world. Okay. So data access, so this locality is frequently found in our application or our program, and then memory hierarchy exploit this data locality, and I will explain why. I will explain the reason. So this slide shows the memory hierarchy in our computer system. So it looks like the real hierarchy in our society, not current society. So you can find the RF. RF means that it's a register file, okay, registers. And then, what is this? You can find cache. So I mentioned the L1, L2, L3 caches. And then, you can find the main memory. So actually, we learned about the register file and the main memory in chapter 2, right? So actually, cache is the new concept of the memory. So you can find the storage here. So this figure shows the memory hierarchy. But as I mentioned, the register file is the capacity of the register file is low. So which means actually when we learned about the register file, actually this file has 32 general purpose registers, right? So actually we can easily calculate the size of this general purpose register. So for example, it's a 4 byte, it's a 30, so we say 32, and then 32. So there are 32 registers. It's the 32 registers. So it's the 128 byte. Right? So 128 byte, right? So it's very, very small. So we already know that in our smartphone, so even our smartphone has 4 gigabyte or 6 gigabyte or even 8 gigabyte of memory. So 8 gigabyte. So giga means the 10 to 9. Okay. Compared to the 128 byte, the 8 gigabyte. So the size of the register file is very, very small. Right? So why? And we learned that our processor access the register file within 1 clock. Okay. And then we learned that, so we already know that the clock frequency of our commodity processor, such as the Intel i5, i7, so it's around the 3 gigahertz, and then recently it is some processors run with the 5 gigahertz of the clock signal. So it's very, very fast. And then it means a processor can read data from registers within 1 clock, which means register file is also very fast. So high performance register file is very fast. So which means that the performance of register file is very high. Okay. So what is the problem? The performance is very good, it's very high, but cost is also very high. Okay. So we are living in the real world. So actually, if our performance is high, which means that the quality is high, so which means that it's expensive, all right? So it is not cheap. So register file is the high performance memory, but size is very small because of cost. Okay. We cannot use the very large good memory inside of a processor. Okay. And then we will not learn about the cache. The cache is the kind of small memory. And then cache is included in the processor chip. So in this figure, the CPU is here, and then actually the cache is included in the CPU. So which means the caches are internal memory. So actually the size of the cache is smaller than the main memory, which is DRAM. Then this cache memory is small, so which means that the performance of a cache is higher than main memory. But the size is also smaller because this included in our CPU chip. Also, it's more expensive than the DRAM, it's main memory. So the size is small. And the main memory. So we use the main memory as like 4 GB or 8 GB of main memory in our computer system. And then, the main memory in all data required by programs. And then, as we saw in the previous figure, the main memory is located out of our CPU chip. So the size is large, but performance will be low. So what does that mean? In the register file, we learned that so we can read data from register file within 1 clock. It's very fast. But when I mentioned main memory, I said, performance of main memory is lower than the register file. Also, it's lower than the cache. It means if we want, if a processor read data from the main memory, it will take longer cycles. So it will take more cycles. Okay. So usually, if we load, data from the main memory, then it will take around hundreds cycles. So which means it depends on the memory traffic, but so also it can take up to thousands cycles. Okay, compared to the register file, it will take very long time. But the size is large. And why did I explain this? Then also I mentioned that the cache is faster and the cache is, but the size of the caches are smaller. So why did I explain this? So you need to connect the locality and memory hierarchy. So locality explains why we use memory hierarchy, why we organize memory hierarchy. So it's like, so what does the locality mean? frequently accessed data. So if a certain data is accessed, then this data will be frequently accessed again and again. Okay, but let us assume all of data is in the main memory. Okay, so let us assume our program accesses variable A again and again 100 times, for example, 100 times. Then let us assume that the latency of loading this data from the main memory is around 100 cycles. Then how many cycles are taken for accessing this A? So it will take 100 multiplied by 100 is about 10,000 cycles, right? What's the problem? Actually, our program frequently use variable A, but if this variable A is found in the main memory, then it will consume 10,000 cycles, right? And then, more cycles are taken, more cycles are taken by our program, then performance is the performance is like the CPI. Performance will be degraded. Performance will be reduced. So that's the problem. So, but we know that if we use the good memory, the better memory, and then if the memory size is very small, then we can access this memory very quickly. So we can think that, we know the A is frequently tested, and then if A is located in the cache, the smaller memory, so let us assume that it takes 2 cycles for accessing cache. Because the cache is the small memory of the cache is located inside the CPU, so we can access, actually the processor can access caches very quickly. Then, if we can find this data A inside our cache, then it will take 200 cycles. Okay? So 200 cycles versus 10,000 cycles. So if we organize memory system in the memory hierarchy, it means we can dramatically, because of the locality, we can dramatically increase the performance of our computer system, because we can store frequently used data inside of the higher level memory. Okay, even though the size of the higher level memory is small, the performance is higher. The performance is better, which means that, and then if we just store the frequently used data in this higher level memory, then we can reduce the required clock cycles for loading this data. Okay, so we can dramatically increase the performance of our computer system. That is the idea of memory hierarchy, right? So this is a very good idea, the computer system.
로드를 했을 때 원클락에 딱 가져오는 거 이렇게 메모리 하이라키로 하면 그것도 데이터 해석이라고.
그렇죠, 데이터 해석. It's a very good question. Actually, in chapter 4, so we learn there are two memories, instruction memory and data memory. So and then we assume that it takes 1 cycle for reading data from the instruction memory and data memory, right? So actually, we can complete the instruction fetch within 1 cycle. Also, we can complete the memory stage within 1 cycle, right? But actually, this is cache. Okay, not a real main memory. Okay, actually this is a cache memory. Okay, so size of this memory is smaller than the main memory. So, and then I mentioned that cache is faster than the main memory. So, which means, so and but the size of the cache memory is small, so which means that if our data is not found in the cache, then it will take a very long time. Which means, oh, so that also the load instruction is executed, but the data is not found in this data memory, the data cache, it's called the data cache, then it will take a very long time. Then load instruction need to be stored in the memory space. So it's kind of a hedging. Okay. So as I mentioned, we cannot use the perfect memory. So perfect memory means the size is very large, and then the performance is very good. Also, the cost is very low. That is a property of perfect memory. But we do not live in the perfect world. So it's a, we cannot use the ideal memory. So we organize the memory system like the memory hierarchy. In order to exploit data locality, right? So as I explained, certain data is frequently accessed by a program, and then if this frequently accessed data is found in the high level memory, then we can reduce the performance. Okay, that is the idea of memory hierarchy. It's very critical. It's very important topic, and it's a very important idea of the computer system. Okay, so this is the also the overview of memory hierarchy. So this is the processor, and also we can find the small, higher level memory. Okay, so this is a higher level, and then this is lower level. Also, we can find large, lower level memory. And then I mentioned that this higher level memory is fast, and then the lower level memory is slow. And then the size, the higher level, the size of a higher level memory is small, and then size of low level memory is large. So it means if a processor requests a certain data with the load instruction, okay, load instruction requests data to the memory, then processor first access the higher level memory, so for example, cache. So I frequently use this $sign for cache because the pronunciation is the same, right? Okay, so when the processor executes a load instruction, then this load instruction first accesses the higher level cache. If this cache is called the level 1 cache, okay, it's a higher level cache. But the size of the cache is small, so which means that the request data can be found in the cache or not. Right. The size is small. We cannot store every data inside of the cache because the size is small. So we just store the frequently accessed data. So, this is the estimated. So we just store the frequently requested data, which means that so we just estimate that this data is frequently accessed, so we store this data in the cache. So which means when the load instruction requests the data to the higher level cache, this data can be found or not. There are two cases, right? And then if the request data is found in the cache, then we call this event hit. So hit. It means that the weakest data is found in the higher level memory. So it means cache. The level of cache, whatever is cache, the higher level cache. So another event is that, oh, weakest data is not found in the cache. It's called the miss. Okay, so there are two events because we use the memory hierarchy, and then when the processor first accesses the higher level memory, so which means the request data can be found or not. So if the request data is found in the cache, then we call this hit. Okay, and then in the hit case, then a cache provides the requested data to the processor. Okay, and then it is very fast. It will be very fast. So, processor can receive the request data very quickly, and then this data is stored in the register file. Then the processor can execute next instruction, right? But in the miss case, the request data is not found in the cache, right? Not found in the higher level memory. Then this request is given to the lower level memory because the data is not found. And then we know the size of the lower level memory is large. So the request is given to the lower level memory. So and then we also check if the request data is found in this target memory or not. And then if the data is found, then the data is given to the higher level memory. And then the data is also given to the processor. But in the miss case, the data is not found in the higher level memory, which means that the data will be found in the lower level memory. So it will take longer time. So processor needs to wait more cycles if the data is found in the low level memory. So you need to remember that hit or miss event in the memory hierarchy, which means that if the data is found in the cache some higher level memory, then this event is called hit. Then if data is not found, then this event is called the miss. So then we can calculate the hit rate. Hit rate. So hit rate is actually it's simple. So hit rate means that it's the number of hit over number of total accesses. That is the definition of hit rate. Okay. So then when we organize the memory system or when we design the memory hierarchy, then we need to increase the hit rate. Right. If the hit rate is low, which means that the request data is not found in the higher level cache or higher level memory. So which means then the request is also given to the low level memory, but which is very slow. So performance, the processor needs to wait longer cycles. So in order to increase the performance of our complex system, the processor needs to wait shorter cycles, which means that we need to reduce the cycles by our program, which means we need to increase the hit rate. So it's very critical for the performance of our complex system. The hit rate is also a very critical performance metrics. Okay. And then, so I will explain the memory technology briefly. So we learned in the computer system, we organize the memory hierarchy from register file to cache, to the multi-level caches, and then main memory, and then also there is storage. There are storage systems in our computer system. Right? So we can also store our data in the SSD or hard disk drive. But different memory levels use the different memory technology. Okay, so I will briefly explain about the different memory technology in our computer system. So these are some different kinds of memory technology we use in our computer system. So static RAM is called the SRAM. Then actually we processor includes the SRAM, so which means that these SRAMs are included in our CPU chip. Okay, oops. Okay. So these SRAMs are included in our CPU chip. So which means the SRAM is very fast. So actually the first these numbers represent the access latency, so which means that it takes 0.5 nanosecond to the 2.5 nanosecond to read, to access SRAM. Okay, it's an aspect here. So SRAM is very fast, but SRAM is also expensive. Okay, so the SRAM is included in our CPU chip, so which means the size is also small. Okay, so SRAM is the good memory. It's the best, but it's expensive. So we use the this SRAM as for the cache. Okay, so in this figure you can find that the cache is here. So actually for this cache we use SRAM. Okay? And DRAM. I believe you are familiar with the DRAM because DRAM is manufactured by Samsung or SK Hynix. Actually, when we mention the semiconductor industry in Korea, South Korea, then actually that means the industry of DRAM, and also essentially these two companies also manufacture flash memory, but usually the semiconductor technology, the leading semiconductor technology in South Korea is the DRAM technology. So if you see this DRAM, then you can find the latency of the DRAM is 50 nanoseconds to 70 nanoseconds. So actually 1 nanosecond is the 1 gigahertz, right? It's a clock frequency. Then if you see the latency of the dynamic RAM, the DRAM, then which means, in order to access the data in the dynamic RAM, then if we use the 1 gigahertz clock, then it will take 70 clock cycles. Okay? So it's just slow. It's just slower than the SRAM. Okay. Also, in the computer system, the DRAM is located out of a CPU. So that's why this DRAM is called external memory, and the SRAMs are called the internal memory. Okay, the external memory. And then if a certain components are located out of a chip, out of a processor, then it will be also slow. Okay, that is out of a chip. So the access latency is high. That means that it's slower than the SRAM, but it's much cheaper than SRAM. Okay, and then we use the DRAM as the main memory. and magnetic disk. Which means actually we use magnetic disk as the hard disk drives. Okay. So if we see the access latency of the magnetic disk, oh, it's very large, it's very high. So it means that the magnetic disk is extremely slow. Okay, it's millisecond unit. So 5 milliseconds means, oh, I cannot calculate. So which means that if the data is read from the magnetic disk, it's a hard disk drive, then it will take very long cycles. Okay, but cost much cheaper than the DRAM. Right? Okay, so that is the summary of memory technologies in the computer system. So if you see these properties of different memory technologies, you can find that fast memory, very, very expensive. Slow memory, it's cheap. So we cannot find perfect memory in our real world. So actually, ideal memory means that we require the access time of as well, so that's fast. And then we also require the capacity and cost of magnetic disk. So which means that if you use the hard disk drive, you can find that the size, the capacity of the hard disk drive is around 1 terabyte or 2 terabytes. It's very large compared to them as well. Actually, if you are interested in the CPU specification, you can find the size of the L1 cache, L2 cache, L3 cache. So actually, the size of the L1 cache is around 16 kilobyte to 32 kilobyte. Okay, it's the size of the L1 cache. And then size of the hard disk drive is almost 1 terabyte or 2 terabyte. So very nice. So we require capacity and cost of the magnetic disk, but we also require the performance of it as well. But it's not possible. So that's why we organize the memory hierarchy, right? And then with the memory hierarchy exploits the locality. So which means that if the locality is not observed in our application, we cannot utilize the memory hierarchy, right? So which means that our data is not, once the data is accessed, and this data is not accessed again, then we cannot utilize the cache, okay? Because the data is always requested from the DRAM or magnetic disk. Okay, but because the locality is observed in our program, we can utilize the memory hierarchy.
PC에서 못 찾는 건 기대는 거
And
노드들 주소값을 받아서 데이터를 가져오는 건데 데이터가 어떻게 그게 내가 원하는 것인지
그거를 이제 배울 겁니다. 좋은 질문이고요. 그래서 이제 어떻게 이제 캐시, 그러니까 how to organize cache and how to access cache. So we will learn about how cache works. Caches work in our computer system. Right? 그래서 배울 거고요. 중요한 토픽이고요. 배울 겁니다. So actually, you can so I will briefly explain about the DRAM technology. Actually, so memories look like this, like the word line and then bit line. So which means that if the a certain word line, so actually we activate the certain word line with the address. Okay. So actually address is given to a DRAM or a memory, then memory decode this address and then activate the target word line. And then if a certain word line is activated, then we can read the stored data via bit lines. Okay. So actually, if we just see the inside of the DRAM, then we can find that this is the word line, and then this is the bit line, and then this is circuit. So actually, the data is stored in this capacitor, and then if the word line is activated, then this is turned on, then we can read the data. But it's the kind of low level of knowledge, so I skip this part. Okay. So this graph shows the capacity of DRAM and then cost of DRAM per gigabyte. So actually, as the technology advances, and also we can use the zero DRAM. So it's which means that the capacity is also increased because, as I mentioned, the DRAM cell is composed of like this. So actually, this is the transistor. It's an NMOS transistor. So and then in chapter 1, so we also learned about the Moore's law. Okay, so it means that when Moore's law represents that, so we reduce the we have reduced the size of transistor, right? So because of this size of this transistor is reduced, then which means that in the same area we can include the more memory cells. Okay, so which means the capacity can be increased. So capacity is also increased, but the cost is decreased. So actually, I will skip this one, but I hope you can understand this one. So actually, DRAM, what all memory is slow. It's slow, but processor is fast. Okay. And then actually we learned that processor reads data from the memory. Okay, the processor requires data for executing instruction, but processor needs to receive data from the memory. Then what's the problem? Problem is that this one is very slow. This one is fast, but without data from the slow memory, processor cannot execute instruction. Then problem is that the performance of a processor is determined by slow memory. Why? In order to execute the instruction, then the processor requires data from the memory, but memory is slow. So it slowly provides some data to the processor, and the processor works very fast. But because of the slow memory, the performance of the processor is bottlenecked by its memory. And then actually this is called the memory wall. Because the slow of the memory, because of slow memory, the performance of processor is actually bottlenecked by slow memory. It's called the memory wall. Then how can we solve this issue? Actually, we require some task from the slow people, but we are very fast, then how can we solve this issue? So because of the slow people, like slow memory, the processor needs to wait many cycles, many times, so longer time. Then how can we solve this? Actually, so this memory is slow. Actually, I said that the memory is composed of bit line and then word line. And then in order to read the data from this memory, then the processor used some lanes, so wires, because this is the electric signal. So actually, the processor reads the data from the memory through the bit lines. So which means that the amount of data read from the memory is determined by width. So which means the number of bit lines, the width of this memory bits. Okay, so we can organize the system like this. This is the memory, and then this is the memory bus, so which means it's wires that connect the processor and the memory. And then we can organize the system like this. And what's the problem? And then this bus line, the width of the bus is same to the width of the memory. The problem is that, oh, memory is very slow. So, and then this part is very fast. Problem is that because of the slow memory, processor needs to wait many cycles. So even though, so in, for example, so it works like the 100 megahertz, but it works with the 1 gigahertz. Then in order to read this one data, one packet of data, then processor needs to wait 10 cycles. Okay. So then you can use the wide memory. So wide memory means that from the one axis, then the width of the memory is larger, so it's wider. So with the one axis, we can read the larger amount of data from the memory. It can be possible, right? So because the memory is slow, then we can use the larger memory, which means the wider memory. And when we access the memory once, then we can read the large amount of data from the memory. That can be possible. In order to increase the performance. The problem is that it's expensive. So actually, when we organize the hardware, we also need to focus on the cost for hardware. It is because memory is wide, and then also this memory is located out of CPU, actually, which means that we need to connect the memory with the external wires. Actually, the external wires are very, very expensive. Okay. So in order to increase the performance, so because the memory is low, in order to increase the performance, then we can use the wider memory. But wider memory is expensive. Then what is the possible solution? Processor is very fast, and the processor is very fast, and the memory is very slow. Oh, it's the first one, and the first one, and then it's the slow one. And then we know that, oh, because of the slow people, slow worker, then this worker needs to wait many cycles, so it's a longer time. The possible solution is that we can increase the number of slower workers. All right. So let us assume that this is the 1 gigahertz, and then this is the 100 megahertz. So Then processor with the 1 gigahertz clock, the processor gives the request to the this memory first, the first clock, and then in the second clock also the processor request the gives the request to the memory 2, 3, and 4. Then it looks like this. Oh. The first processor gives request to the flow memory, so it takes very long time, but there are many memory blocks. So these blocks are called banks. Okay, so there are many memory blocks, and then the request is given to the first memory block, so bank number 0, and then it will take very long time. But processor does not wait until this data is given returned to the processor. Processor gives the another request to the different bank. It is possible because it works very fast. Then it will take very long time, but the request is given to the another bank. It will take very long time. So, but these memory modules, the memory banks, work in parallel. Okay, because the request is given and then the request given to this memory bank, it's working, and then also given to this memory bank 2 or memory bank 1, then it's working again, working like this. So by doing this, we can utilize the slower memory module, and then this technique is called the bank level parallelism or memory level parallelism. So which means that because the memory is slow, but the processor is fast, the request, the memory is organized as multiple modules or multiple banks. The memory bank represents the independent memory module. So the request is given to the multiple memory banks. Then processor can request give this memory request very fast, and then multiple memory banks work in parallel. Then it's done. Then the data is also given returned to the processor serially. Okay. So modern processors use this model. So actually the memory is composed of multiple banks. Okay, the independent memory module. Then processor can give the same actually request to the multiple banks to the slower memory. Then processor can also receive the data. Okay.
그래도 순차적으로 있으면
그렇게 줘야죠.
한 번에 처음부터 같이
그래도 이제 이 버스가 지금 이게 위스가 이제 작잖아요. 내려가잖아요. 그렇기 때문에 리퀘스트는 한 번에, 그러니까 어차피 이제 메모리에서 읽어올 때도 이게 한꺼번에 가면은 지금 여기서 보면은 이게 이제 메모리가 이제 모듈이 여러 개니까는 한꺼번에 가면은 이만큼의 데이터를 다 한꺼번에 읽어야 되잖아요. 그러려면은 그 버스가 위스가 작기 때문에 그건 불가능하고, 그러니까는 순차적으로 첫 번째는 이렇게 갔다가 두 번째 이렇게 가면은 얘 읽어오는 속도가 첫 번째 가면은 이렇게 될 거고, 두 번째 가면은 이렇게 될 거고, 세 번째 가면 이렇게 될 거잖아요. 그러니까는 그 순서대로 이렇게 한 번, 두 번, 세 번, 네 번 이 네로우 버스로 이렇게 읽어낼 수 있는 거죠. sequential. This is the very good. Actually, this is a very good technology. Actually, in the real world, you can also apply the same kind of approach. Okay. So there is a fast worker and then a slow workers, and you can also use hire the many slow workers to increase the performance. And that also, I will explain about the flash storage. So recently we use flash memory as the medium of hard disk, the storage device. Now, and then if we use the flash memory as the medium of storage, then this storage is called the solid state drive, like SSD. Right? So, actually the flash, unlike the magnetic disk or hard disk drive, the flash storage use the flash memory, so which is the chip, right? It's a semiconductor chip, so which means that it's very fast. It's faster than the magnetic disk. Is that because so if you see the this magnetic disk, the magnetic disk has includes the motor, and then actually the magnetic disk has it's a platter. It's called the platter. So like it's a one bar, okay, and then actually the data is stored in the surface of platters, okay. So because the in this magnetic disk, then the motor rotates the manipulator, and then actually not to find the leakage data on the platter, then it's called the surface. And this header needs to move around on the platter. So that's why the magnetic disk is called the mechanical drive. It's a mechanical drive. And then if we use the mechanical devices, then it's very, very slow. That's the problem of hard disk drive, because we need the motor rotates the platter, also the header of this arm needs to find the weakest position of the data. So it will take very long time. But if we use the flash memory is a chip, which means that just an electric signal is given to a flash memory. And then we can read the data from this flash memory. So flash memory is very fast. It's 100 to 1,000 times faster than disk, but it's also expensive. It's more expensive than hard disk drive. Also, but the performance of the flash memory is lower than the drive. It's obvious, but it's faster than the hard disk drive. So we can use the flash memory as the media of the storage system. So recently, our computer system and then our smartphones include the flash memory, and we use the flash memory as the storage devices. And then hard disk drive, that is the storage, it's very, very slow, as I explained. Okay, so it's around the millisecond latency, so extremely slow. So we can think that this is storage is the extremely slow. Okay. So as I mentioned, in the computer systems, we can use the various types of memory technology, but as I also mentioned, the performances are different. Also, the costs are different. Okay? And then because of these diverse characteristics of memory technology, then we need to organize the memory hierarchy also. Actually, in the higher level of the memory hierarchy, we use the expensive memory technology. So the size of this memory is small. Then in the lower level of the memory hierarchy, the cost is very low, which means that we can use the larger memory but performance is extremely low. Okay, so it means that if the data is found in this low level memory, like the storage, then our computer system will be very, very slow. Okay, that's why we are using the memory hierarchy. Okay, so I will briefly explain about the cache. So cache is located in this is the register file, and then the cache is, then so this is the memory, main memory, the DRAM. So cache is located between register file and then main memory, the memory hierarchy. Okay, which means that, but when we learned about the instructions in chapter 2, so when we learned that our instructions change the register file and then main memory, not cache. Right. So when the load instruction is executed, there is a load of like load word, then load word reads data from the main memory and then transfer this data to the register file and then store it. The direction is inverse. When I mentioned about the load or store instruction, I did not mention cache. Okay, so actually the caches are temporary memory. Okay, the instruction just changes register file and the main memory, not cache. Caches are temporary memory, and that is cache is managed by hardware, not software. So which means, so actually some hardware also provides the privileged instructions, so special instructions they can manage cache, but these instructions are special instructions. Okay, normal instructions does not manage cache. Caches are automatically managed by hardware. So you need to understand. With the instructions, we can change the data in register file and main memory. So which means I will explain that we instructions changing the state of the instructions changing architectural state in the computer system. The architectural state means register file and main memory. But performance is also very critical in the computer system. And then as I explained, so we cannot use the perfect memory technology. So in the computer system, we can find the cache, okay, cache here, and then this cache is the temporary memory space. And then caches are managed by hardware. Okay. Okay. Let's see the meaning of the cache. So if you find first the definition of cache in the Google, and you can find this one. So cache, what is the cache? It's not cache. Okay, it's not cache, but the pronunciation is the same. So cache. The cache means the hiding place. Okay, in the normal world. So it is just like the some 금고, right? It's the hidden 금고 is called the cache in the real world. But we need to focus on the definition of the cache in the computer system. So you can find the definition of the cache in the third line. So what is the cache? It's a temporary storage space or memory. Okay, so you can see the temporary. Okay, that allows fast accesses to data. So that is the purpose of cache. It's the purpose. So why do we use cache? Not increase the performance of memory system, which means not increase the performance of computer system. We use the cache, okay, temporary memory space. So in the next class, I will also explain about the the detailed behavior of cache. Okay, so this is also very important part of this course. Okay. Okay, any questions? Okay, thanks for your attention. See you the next time.